All right. So last class we left off talking about measures of central tendency. Okay. So today we're going to talk about measures of dispersion. Now, one thing I want to mention before you go in the class, I posted the first Excel assignment up on Canvas as well as the first Connect assignment. You'll notice the Connect assignments due a couple days after that Excel because we still have, I'm guessing we won't even quite get everything covered by the end of this week. We might have to do a little bit on next Monday. But we've done quite a bit where you can get a pretty good amount of that Connect homework done. If you do start working through it and you get up to things like weighted means, you can stop at that point, right? We haven't covered weighted means. We actually haven't covered kind of variance, things like that. And that due date's quite a ways out. I think it's the 16th of September it's set for. So we've still got quite a bit of time. Once we've covered all the material, you'll still have at least a week, week and a half to get through that, okay? Are there any questions before I kind of jump into things here from you guys regarding anything? Okay, jumping in the chat. All right. So the first measure of dispersion that we have, we're going to talk about, is the range. So the range is pretty easy. You've probably seen something like it before. All we're going to do is take our data set, look for the maximum and the minimum, right? Once I find my maximum, here it's 90, find the minimum is 20. I'm just looking for the difference between those two, right? It's going to tell me, the range of the data. So 90 minus 20 here gives me 7. Okay? Now that's all fine and well. Like the range, it does tell me, like, if I had a data set that was from 1 to 10, I know there's a lot less variation in that than if it went from 1 to 100. Right? But the problem with just using the range is, let's say I had the same exact data set, but every single observation was 20, except for the one that was 90. Right? Well, what would the range of that data set be? Well, the maximum is still 90, the minimum is still 20. It would have the exact same range as this data set, but there's a lot less variation because 6 of the numbers are all 20. They're the exact same thing. So we need another, like a better measure to capture this, okay? Actually, let me make sure. All right. So what that measure is going to be is our population variance, okay? So the population variance, we're going to denote with sigma squared, right, this Greek letter. And I'm going to describe to you what this formula is. And I'll have some data sets and we'll work through, I'll go through some examples later. But I just wanted to try to describe in words and start to get familiar with how we write some of these things notation-wise. So what we're going to do, just like with the mean, this summation sign means everything to the right of this summation sign due for every single observation. So for every single observation, starting with the first observation, we're going to take the value, whatever the variable we're looking at is, for that first observation. We'll subtract the mean. We call that the deviation from the mean. Once we have that deviation from the mean, we're going to square it. And then we'll go ahead, go down to the next observation, take the second observation's value for that variable, subtract the mean, square that deviation, continue all the way down until we get to the very last observation in that population data set. Once we get there, we're going to add up all those deviations squared, right? All those deviations that we squared, or all the differences from the mean that we squared, we're going to add up all those values. That's our numerator. And then the last thing we have to do is divide by the total number of observations in that data set. Okay? Now the sample variance is going to be the exact same thing, but remember we denote the sample variance with S squared, right? Greek is population, kind of our English lettering is a sample. Here was our population mean. We're still looking for deviations from the mean in the sample variance. It's just now we're using the deviations from the sample mean, right? Just notation. The actual process, once we start plugging the numbers in, it won't look any different. So we do the same thing here, and instead of capital N, which represents the total number of observations in our population data set, lowercase n represents the total number of observations in a sample data set. All right? And then once we add up all those deviations squared, now there is one difference that isn't just notation. So the sample variance, and we'll probably talk a little bit more in depth about this once we get to things like confidence intervals and hypothesis testing. but it's always going to be a biased measurement of what the true population variance is. And so without going too in depth into it, because it's biased, we have to correct for it by, instead of dividing by n, we divide by n minus 1. Okay? Like the actual proof of this and kind of the reason as to why is probably outside the scope of this class. But the general idea is that, and as I said, once we get to talking about confidence intervals, this would make a little bit more sense. But we always know there's going to be a bias, and so we correct for that bias by dividing by n minus 1. Okay? The units of measurement for our variance will be whatever the units were for the variable we started with, right? So if it's salary data, it would be dollars. If it was height data, it'd be centimeters or inches or however we measure it. Okay. Any questions on this before we keep moving? Like I said, I'll work through a data set to show you the exact process, but this is formulas we'll be starting with. Okay. Let's see something in the chat. All right. So this is just kind of writing out those steps. What's the very first thing we'll need? Well, if we're looking for deviations from the mean, we first need to calculate the mean, right? Then, once we have that mean, we'll go ahead and subtract it from each observation. We'll then square all those deviations, all right, those differences from the mean. Now, we could combine steps 2 and 3, right? I could, for each observation, subtract the mean and then square that value. I don't have to, subtract the mean from every single observation and go all the way back up and square all the values. I can do it all at once, right? But I really can break it down and technically use 2 different steps. Once I have all those deviations squared, I can add them all up and then divide by n for a population or n minus 1 per sample. Right? This is the process we're going to use. Okay. Let's look at some actual data. Actually, no, we're not. I'm going to say one more thing before I go to actual data. I mentioned we're not only going to calculate the variance, we're going to also calculate the standard deviation. Really, there's nothing different going on here. So the population standard deviation is sigma. The sample standard deviation is lowercase s. But all the standard deviation is, it's the variance scaled. And how are we scaling it? We're taking the square root of it. So notice this equation looks identical to the equation for the variance. So what we're really doing is we're finding the variance, and then to get the standard deviation, we're then taking the square root of that variance. Right? So the process would be exactly the same. It's just you have one final step with the standard deviation, which is take the square root. Okay. Same thing for the sample standard deviation. It's just the sample variance, but we're going to take the square root of it. And this scales it. We see the standard deviation in a lot more formulas that we'll use throughout the semester. And especially with confidence intervals and hypothesis testing, we're not going to be using the variance, we're using the standard deviation. And so I just want to get practice kind of using both of them and seeing the difference between both of them now. Like I said, it's really the standard deviation is just the variance scaled down a little bit. Okay. So for example, if you had a variance of 100, the standard deviation would be the square root of that, which would just be the square root of 100 is 10. Okay. So let's start out with this data set, which is head football salaries, head football coach salaries. Okay. This is old data. I forget what year this is from, but it was Ball State. We've got the head football coach all the way down to the video tech guy. We can think about this as a company, CEO down to the janitor, right? We've got some people paid a lot more, some people paid a lot less, right? So this could be any salary database, and we might want to say, what's the variation, right, in this data set? We could compare it across, right? If I can do this for a bunch of different companies, I could then compare across those companies. Okay? So how would I start to find the variance? Well, what's the very first thing I need? I need to know the mean, right? I need to know the deviations from the mean. Well, I can't do that if I don't have the mean. So we did this last class, pretty easy. How would I find the mean here? Just add up all the salaries and divide by the total number of observations I have, which if I count this, I believe it's 10. Right? So we'll add these up, divide by 10, or you can kind of see here, oops, I wrote all that out, right? That's kind of review from last class, but it is the first step we need to do. So now that I have this mean of 134.5, I can kind of see, well, these values vary a lot from that. Right? This value varies a lot. If I look at the deviation there, it's going to be really big. If I look kind of at some of these values, 124, 150, those don't vary very much from that mean at all. right? When I subtract 134.5 from this and square it, it's not going to be near as large of a value. Okay? But if I write that out, it's going to look something like this. I'll come back to this slide in a second. I want to show you this, okay? So what I would do is I'd go through every single observation, 489 minus that 134.5, square it, write that number down. 150 minus 134.5, square that, write that down. Do that for every single observation, right? Once I do that for every single observation, I'll add all those deviations squared up. And then what's my final step? If I treat this as population data, because I have every single coach that was on salary there, I would take the sum of those deviations squared and divide it by total number of observations n, and get a variance of about 14,000. Okay? I want to go through, we're going to kind of go back. If I wrote all of this down, right, not just the numbers, but what I actually did within each one of these cells, that's what this is, right? That head coach's salary minus the average squared, plus the next highest paid coach's salary minus that mean squared, plus so on and so forth, all the way down to the video tech guy. I add all those up, and I divide by 10. Another way of writing that, which is here it looked a little bit cleaner, but once we move to other things in the semester, we'll see it written multiple ways. If I divide something by 10, it's the same as multiplying by 1 over 10. No, you're thinking of like square roots, right? Yeah. Okay. All right. See if there's any questions here. Okay. So here I want to mention a couple things about the variance, right? Just some general properties. I wanted to give you the formula, see how we might kind of do it in practice with a data set. So let's go back and look at the actual formula. Okay, so if we look here, what's going to happen every time I see a deviation from the mean? Well, if something's above the mean, then when I subtract the mean, I'll have a positive value. When I square that positive value, I'll still have a positive value. Now, the further that value gets from the mean, the larger the value it's going to add to that numerator. So observations that are really extreme, really far away from like the middle central point of the data set are going to add a lot more to the variance than values that are really close to that mean, okay? So the variance is going to be a measure of across the entire data set, how much the observations are varying from that middle point or that central point, okay? Now, what happens if something's below the mean? Well, then when I subtract the mean from that, I get a negative value, but when I square that, it then becomes positive. So it doesn't matter if I'm 50 above the mean or 50 below the mean, it adds the same amount to that variance, because the variance isn't telling me which way the variation, is above or below the mean. It's just saying, no, anything that's away from the mean is adding to this statistic that measures the variation in the data set. Okay? So that's kind of one thing that square kind of does for us. The other thing is it really over penalizes really extreme values. So think about it this way. If I had something that was 1 away from the mean, when I square that, what gets added to the numerator of the variance? 1 squared is just 1. But if I'm 2 away from the mean, and I square that, I don't just add 2 to the numerator, I add 4. And instead of 3, I would add 9, right? As I get further and further from that mean, when I square it, it blows the number up even more. And so it really over penalizes. I shouldn't say penalize, but it really it puts a higher weight on those values or on the observations that have values way above or way below the mean. Okay, so this is kind of how our variance is calculated, just some properties and some traits about it. So if we look at that data set that we had here, notice the value really far away from that mean adds a huge value to that variance. Values really close to the mean add very, very much smaller amounts to the variance. And then it doesn't matter if they're below or above the mean, they still add positive value. Excuse me. Okay. Any questions on that before we keep moving? Had one sitting here. How do we know when to use? So the question is, how do we know when to use the population or sample variance? It's you will be told whatever data set you have that it's either sample data or it's population data. So it's not like you are choosing between the two. It's whatever data you have, that's the equation that you have to use. You have population data, you got to use the population variance formula. If you have only sample data, you'll have to use that sample variance formula. And on any homework or excuse me, exam questions, I'll even usually like make it very clear what type of data set this is. Excuse me. I'll bold the word sample or I'll bold the word population so it's very clear what data you have. Okay, this is a good question. Any other questions before we keep moving? Good, chat. Okay. So if we take that sum of the deviation squared, divide by the total number of observations, we're going to treat this like population data, we get about 14,000. Okay. So another thing we can do is actually there's a second formula. So I always use the first formula because it really captures, oops, sorry, actually I thought my mouse through. I use this formula to start out with because it really captures what the variance is trying to measure, right? Which is the variation from this point of central tendency. Okay. Now you can use this other equation, right? And then what you're doing here is just some more practice reading these formulas. I'm going to start from the first observation and square that value and do that for every single observation. Once I've squared every single observation, I'm going to add those values up. Not the deviations from the mean, I'm just squaring the actual values, right? Once I add all those up, I'll then subtract the number of observations in the sample times the mean squared, okay? So I'm going to skip this next slide for a second. I'll come back. Yeah. This guy right here. Yep. So what is that going to look like with our data, right? Well, I'd go through each salary, 489 squared, write that number down, 150 squared, write that number down. Do that for every single observation, and then add all those numbers up. That would be the sum of the x's squared, or the sum of every observation squared. Okay. Once I have that, the next thing, looks like this got moved over. The mean was 134.51. So I'm going to square that, write that number down. When I then go back to that formula and look at what I needed, I have the sum of the x's squared. I know my n, right, number of observations is 10. The mean was 18,000. So if I plug all those numbers in, I'll get about 147,000. And then the final thing I need to do, just like the other equation, divide by the total number of observations in my data set. So if I divide by 10, oops, sure enough, I get the exact same value as the other method. Right? Now, I said the other formula really gets across more of the properties and kind of what the variance is measuring. But an additional thing is if I try to do it this way, these numbers aren't big enough to where this becomes crazy. But if I actually didn't put these in, like these are in thousands, right? So if I actually included all the zeros, when I square 489,000, that becomes a really big number, right? Whereas if I take 489,000 and subtract 134,000 from it, well, now when I square that, it won't be quite as large. So sometimes using that first formula, it just makes it easier because the numbers, the intermediate numbers that you're calculating aren't as large, right? And if you're doing it on a calculator, that's important because that means you don't have to type as much in, right? So either way will give us the same answer. And we can do this, right? You have this equation for the population and for the sample, variance. You can do either one. Once again, it's really dividing by n minus 1 and dividing by n, but it's the same thing as multiplying by 1 over n minus 1 or 1 over n. Okay. Any questions over that? So I put this slide in here, and sometimes I am in the mood to go through it, and sometimes I'm not. But basically, I told you that those two equations are the same. The first one we started out with, and then the one that we just went through. But I mean, why in the world are they the same, right? Well, it's basically, if you knew some mathematical properties about distributing sums and some rules of sums that I'm not going to expect you to know, and you don't need to know, if you basically rearrange this formula, you can prove that it's the same thing as this, right? And there's some like kind of tricky things they do there. Like, so at first I just take the numerator and I'm like, oh, I can square this, I can get the, FOIL this out or whatever. And then I can distribute my summation sign. And here's like a little trick where I multiply things by 1. It doesn't change the equation, but n over n is 1. And when I rearrange this, well, now I get the sum of the x's squared over n in here, which I know is just the sample mean. So it's just really a mathematical proof of how you would simplify, I guess, this equation down to this, or vice versa, right? I guess I could work in either direction. But I'm never going to expect you to know any of this. If you're interested, if you're a math geek, I don't know, set up a Zoom meeting with me. We could talk about it for a while, or stop by my office or something. Okay? So, we got through there. So let's think about some questions that we could be asked with this sample variance. And these might be something that looks similar to what the question you might get on an online quiz today. Okay? So let's say I wanted to, with that commuter data we used last class, let's say I wanted to find the population variance. Okay? So I want a population variance. How can I find that? Well, if I remember right, last class we found the mean of this data set was 45. So what process do I do? So I start with the first observation. I go 20 minus 45, square that value. So I think what, negative 25 squared is 625 maybe. Write that number down. If I'm doing this by hand, I would even suggest create a column right next to the variable that you're trying to find the variance of, and just write that number in. 625. Go to the next observation. 35 minus 45. So negative 10 squared is 100. Write that down. Go ahead and do that for every single observation. Once we get that, we'd add them all up. And here, if it's population variance, we would divide by what number? 7. So pretty easy. I mean, not super easy. We've never done this before, but at least we're getting used to this kind of repetitive process. Now, one thing that I want to point out here, if I look at the possible answers I have, which one can I rule out right away? So D is so we can't rule out B, but we can rule out A. So what would so if the variance of a data set really was 0, what would have to be true? Well, how does that 0 get added to that numerator? It's only if the observation is equal to the mean, right? Because we're subtracting the mean, the only way a 0 gets added to that numerator is if each observation adds a 0 to that numerator, which would mean every single observation is exactly equal to the mean. So we would have to have a data set, you're right. Here we'd have to have a data set with all 45s. We don't. So we automatically know the variance can't be 0, right? That's really all we can say. Can't really cap things out. I mean, I guess if you had a mind that could really quickly think about deviations and how large things would be, maybe you could put a upper bound on it, but I sure as hell can't do that. So now we just have to actually go ahead and calculate, right? But we can rule out A. What's also true is we would never see, so 0 is actually the lowest variance we could see, right? Because we can never get negative values added into that numerator, and the denominator, the number of observations, will always be positive as well, right? You can't have negative observations. So, sorry, you can't have a negative number of observations, is what I should technically say. So we'll go ahead, we'll go through and do that process, right? I kind of already mentioned for the first few, right? 20 minus 45 squared is 625. Here's all the values. If you want to like work through it and kind of prove it to yourself, we'll then add these all up. And notice there was an observation that was exactly the mean, and sure enough, it added a 0 to the variance, right? Because the variance is a measure of the entire data set. So each observation will have an influence over the variance. This observation says, yeah, if I only looked at this observation, it would look like there's no variation in that data set. But there's a lot of other observations that show me, or there are evidence of, there is more variation in this data set, right? And so once we add those all up, now we have a measure of the variation across every single observation in that data set. And then finally, we divide by the total number of observations in that data set, which here was 7, right? So 414. All right. let's go to the next slide here. So what if I came in and go, you know, I thought this commuter time data was population data. Turns out it's only from one division within that company, right? So it's actually only a sample of all the people that commute to that, you know, building. So if I now say, okay, now I know this is sample data, I have to calculate a sample variance. What do I know has to be true relative to what I did here? The only difference would be, yeah, the only difference is instead of dividing by n, I divide by n minus 1, but none of these numbers have changed, so I'll still get the same sum of those deviations squared. So when I divide by 6 instead of 7, what's going to happen to this value? Divide by a smaller number, it's going to go up, right? So I know that when I calculate this sample variance, because I did this work already, it has to be greater than 414. Oops. So if I look at these possible answers, I don't even have to calculate this out. It has to be 483. It's the only option here that's greater than that previous one I calculated of 414. Now, in most problems, you're not going to calculate a population and sample variance with the same data set. I'm just using this as an example, like, oh, what if we had done it and then figured out we were wrong in our assumption about whether it was population or sample data, and to kind of, you know, show that when we're dividing by n minus 1, it's inflating that variance a little bit, trying to correct for the bias that would exist. Yeah.
So why is it in capital population but it's not?
So why do we use the lowercase n in the sample? It's just notation that notates or that shows that n is the total number of observations in the population. Lowercase n is a subset of that, and so lowercase n represents if we had a sample, that's the total number of observations in the sample. Yeah. And for right now, it seems like why don't we just use capital N both times? Once we get to some future topics, we'll actually be having population. We'll have n and capital N and lowercase n kind of in the same formula. Yeah, yeah. Yep. But that's a good question. Are there any questions in that? For actually, I think we have any time. All right, so I just want to. No, I think I'll waste time, or I'll spend time on something else. I won't waste it here. So we can go ahead and do that, right? Nothing changes here because we have the same data. So when I subtract 45 from 20 and square it, it's still the same value. I go ahead and do that for every observation, add up those deviations squared, and now I divide by 6, and I'll get that 483. Okay? So another thing I want to mention here, or I already mentioned, like if I give you this in an online quiz, if you see a 0 and it's not, every single number isn't exactly the same, or you see a negative possible answer for the variance, right away you should be able to cross that off, right? It has to be positive. And I'll do that a lot of times, even on an exam, if it's a multiple choice question, like make it easier, I'll be like, put a negative value as one of the answers, and right away you can cross it off. Right? Yeah.
Are you doing a calculator on an exam?
Yeah, so we're gonna, so well, we have a calculator. So hold that thought. When we do Excel work, I'm gonna mention something, and this should answer your question. All right. So the next thing I want to kind of go through, just to give us a way to start to think about distributions. Now, we haven't looked at a continuous distribution like this yet. We've created histograms, right, which we can get close to continuous by making more bins, and we just said drawing a line across kind of the top of those rectangles that we're plotting. But I want to start to think about how does the mean and variance influence the distribution, right? So here, I've only used distributions. So what, 1, 2, so there's 6 of them here. Each color represents a different distribution or a different data set. They all have the same mean. So notice, if I try to find the mean of all of these, it's going to be right at 0. They're symmetric, so the mean is equal to the median. We got this nice normal curve. They all have the same mean of 0. If I had a really, really low variance or a low standard deviation, because those things are one and the same, right? Standard deviation just scales it. If I have a low variance, that's telling me most of the observations in the data set will be centered around that mean, right? So if I look at the values that are really close to the mean of 0 on either side, they'll have a high relative frequency. So this y-axis here is going to be the relative frequency. So for these values close to the mean, there's a high relative frequency or a high chance we see values near the mean in that data set. As the variance gets higher, sorry, before I say that, and also if we have a very low variance, notice values that are very far from the mean. So this blue line represents the lowest variance or lowest standard deviation. Values far away from the mean also have really low relative frequencies, right? It's not very likely that we see those values, okay? Now, as my variance and standard deviation increase, what that means is there's more variation in the data. What is more variation in the data? How do we measure that with the variance? Well, it's values that are farther from the mean, right? So when I get a higher variance, that means I have more values that are further from the mean and fewer values really close to the mean. So this gray line here has the highest variance or the highest standard deviation. And notice the values near the mean now have a much lower relative frequency than they did when the variance was low. And values very far from the mean have a higher relative frequency than they did before when the variance was low. So it's almost like when we have a higher variance, it kind of flattens out this distribution because it means that values far from the mean become more likely, values right around the mean are becoming less likely. Okay? Any questions on that before I keep moving? Okay. So one thing I want to do is how do we do this in Excel, right? So I've got this slide here, but I'm just going to go ahead and kind of show you. So I don't have it open, so we'll go to here. My eyes, oh here. My eyes. We'll just use that blank COVID file we were using before. So here was some of the work that we had done. We had things like, frequency, relative frequency. And I think you also might have had we did cumulative frequencies here. So whatever you had, and this file for me got saved at different times because I was using it for multiple classes, but this was just the blank file, right? So one thing I was going to show you, just in terms of organization of Excel files. So I don't want, right, I had cell reference here, I don't want to change, but I want to move all this stuff over. So what I'm going to do is just right click, on the columns and go to insert. I'm going to insert a couple columns here just to give myself a little bit of room to work. And notice all these kind of cell references. If they were using something like over here, it's okay. It automatically doesn't make, just because it's pushing them out to so here, be a little more explicit about this. Notice these are using relative frequencies. We're using column O before. When I insert my columns, well, now it can't use column O, but it was automatically updating that to keep using the same thing. Right? So that's just kind of a nice, useful thing if you're trying to do something kind of quick. So let's say we want to find the 3 measures of central tendency. These are all pretty easy, okay? So for the mode, do the median first. For the median, it's just equal sign median. I will then select that COVID-19 death variable, Control Shift or Command Shift on a Mac, hit the down arrow, now press Enter. It's easy as that, right? Now with a bunch of observations to find the median by hand, I would have had to cross off the highest, cross off the lowest, next highest, next lowest, so on and so forth. That would have taken me a lot more time. So this is a lifesaver, right? Or a huge time saver. Once again, I don't know if I forgot to do this for you guys before, but if I forget to zoom in, you got to yell at me because I know it's a lot easier to see once I zoom in. Okay? If we wanted to do the mode, it's just equal sign mode, and then select that variable. Okay, Control Shift or Command Shift on the Mac, down arrow, hit the Enter key. Ooh, I got a problem here though. So with this data set, I've got each state and the number of deaths they have from COVID. So what's causing probably this mode function not to work right? Huh? Exactly. It'd be a lot less likely with this data set that I have 2 states that have the exact same number of COVID deaths. And that's what's happening. Notice if I change this one to 19, Now it picks up, now the mode function works correctly because there's a value that's repeated, okay? Now I'm never gonna try to like trick you with that. You should just be able to use the mode function, no problem. If I ask you to do that. For the mean, you would think it'd be equal sign mean, but Excel calls it the average, kind of the more non kind of statistics way of that what we talk, right? So average mean means the same thing in Excel. So we'll select that COVID variable, hit enter. Now I've got my mean, my median, my mode. So on average, 2,600 people kind of are dying in each state. But notice that's the mean, that's a measure of central tendency. But if we look at these observations, right, Alaska only has 19, and where was that 8,000 I just saw? Florida's got 8,000. So we know there's quite a bit of variation. So let's try to find the variance, and the standard deviation. So to find the variance, it's simply going to be var dot, and we'll treat this as population data since it should be every recorded COVID death. So var dot p will find the population variance. Var dot s would use that sample variance equation, right? And it's essentially using the formula. It's doing all the work behind the scenes for you, okay? So we'll treat this like population data. Select that variable. And now we got our variance, okay? Now, if I wanted to find the standard deviation, I've already got the variance. What's something I could do? I just take the, I said we're, so I said to get the standard deviation, we're just scaling the variance. And how are we scaling it? We're just taking the variance and then we're going to take the square root. Right? So the square root function in Excel is sqrt. We'll be using this at other points, to take square roots. So I want to introduce it now. And then we just want the square root of the variance, right? So I click on that cell that has the variance in it. I hit OK. Now what I could also do is, there's a built-in formula that if I didn't find the variance already, it'll find it and take the square root, which is stdev dot p, right? Standard deviation. And then P represents population. If you're finding this population standard deviation, similar to the variance, dot S would be for a sample, okay? But once we have that, I just select that variable, and sure enough, I get the exact same answer, right? I mean, this is rounded here. I can go to format. All I have to do is put a number, increase the number of decimals, maybe. There we go. Notice it's the exact same number, right? It's just formatted a little bit differently the way that we can view it, okay? Any questions on any of that before we keep moving forward here? We're okay? All right. Now, one thing that I want to mention in Excel as well, I forgot to tell the other section this, but I will. So on the Excel homeworks, I want you to turn in, so I know there's a Word document that kind of has the questions, and then there's the Excel file. What you should be uploading is for sure uploading an Excel file with your work that you did in Excel, right? You can't just put your answers in a Word document and upload that. That won't get you full credit. You need to submit to me the Excel file that you did the work in, right? Now, if it's easier for you, you want to, it makes it a little bit easier for me. When there's a question on an Excel homework that like you need to like type a sentence out or something for, well, typing in Excel is really annoying, right? Because if I type really long stuff, then like I can't see it here. And if I try to format, I'll merge cells. It's just not as easy to type in. So if you want to do all the Excel work and then submit that file, but anything where you have to have like a written response, a typed response, you want to put that in a Word file, you can upload both files, okay? So that's how we'll go about that. The other thing in Excel that I don't think we'll run into it in the first assignment, I can't remember the exact data set now, so we might, but when we're dealing with things in Excel, one issue that we can run into is, so let's say I have something like 0.5, and I know that is going to be, let's say that's my relative frequency, and I want to make it a percent. So actually, I'll pull up the complete version because that one has, yeah, here we go. We added this percent frequency here. So what I don't want to do is, let's say instead of multiplying this by 100 like I did, let's say I delete that and I just say, okay, it's the relative frequency, but it's times 100. But I also know that if I go to up here, I can just format it as a percent. Oh, okay, that's all I need to do. The problem is what's in that cell, even though it's displaying as 69%, right? If I try to use other formulas, particularly the variance formula, right? It's not going to quite. Is it the variance? Hold on, is it? Oh, you're right. There, that. I'm gonna say something really funny. So maybe it's not the variance. What equation is it? Oh, that's not variance. I know what it is. If we were using that count ifs, right? And we were trying to check to see, is this number less than, say, 70, right? It won't work correctly. It kind of treats it though it's like 0.7. So let me see. If I go, let's do a count if. I know we haven't used that, but it's only checking one. So let's say count it if this is greater than 10, right? Whoops, greater than 10. So this works very similar to that count ifs. It just is only checking one thing, right? So if I look at this, how many should be, sorry, I did less than. How many are less than, oh, I need to do greater than. How many should be greater than 10%? 2, right? Why is it telling me 0? Because what it's actually using, this is just formatted differently to display as a percent. In the cell, it still is 0.69, 0.13. So notice if I go count it if it's greater than 0.1, now I get that 2, right? So it's just a really bad habit to start. I mean, sometimes it's nice because you're trying to show someone, display, you know, the percentage to them. But when you're using that value in other formulas, sometimes you can run into these issues. That's why I just always, you know, take the relative frequency and multiply it by 100. Now notice I have this formatted wrong. I don't want it as percentages anymore. I just want it as a general number. And so now I get my percentages. It doesn't have the percent sign there, but at least when I use other equations, now it'll work. So now notice if I use that 10, now I can get that there's 2 above it. Right? So that's something we can kind of run into. Like I said, I don't think there's anything on the first assignment, but potentially down the road. When we want to see a percent in here, we should be multiplying that by 100 instead of just format changing it. Okay? Any questions on that? Yeah. Oh, yeah. So if you have that greater than, there's 2 ways you can do it. I would probably do it the second way. You could just use this count if formula, right? And say, is it greater than whatever the maximum I told you was? Or since you have everything set up with a min and max of the bin, and it's a lot easier to just copy all that down into, for the very last one, you have to use only count if. And for the very first one, I think, you have to use only count if. For the first one, if it's less than, say, 100,000, set the minimum at 0. Then you can use the count ifs and just copy it down for everything else. And for the last one, let's say here I want anything greater than 25 or 12,500. I could just like put a crazy large number in there that I know is greater than the maximum of my data set. Does that make sense? Yeah, so the question there was on the homework. I believe both the first and the last bin are like open-ended. So the first one is like anything below a certain amount, and the very last bin is anything above a certain amount. There's like no cap on it. So you can set it up the same way we did in class before, but just use an outrageously high maximum for that last bin. Okay. Any other questions on that? Probably end here. We're good. Okay. So that Excel and Connect homework aren't due for quite a while, but I would start because they're running at the same time. And also, if you wait to do that Excel, I'm telling you, either they're not going to get done or you're going to get not much on it. I would start working on those now. Okay. We've done everything that you'll need for the Excel one, the Excel homework, but the Connect homework, we still have a little bit more to cover kind of on Friday, and maybe a little bit on Monday. So those due dates are quite a ways off, but I'd start working on those now. Okay. Do you have any questions on those? Haven't had, like I said, I think last class, haven't had anyone set up like Zoom meetings to go over things, but as you're working on those, feel free to email me, set up a time on Zoom where we could like work together. Like I said, the Excel file, I think actually working on Zoom will be even better because we can share each other. I can have you share your screen with me as well. And I can kind of see what problems you're running into or like point things out. Okay. Other than that, everybody in group one, I'll see you again on Friday if you want to show up in person. For those of you here today, next week will be when you get to show up twice. So you'll show up next Monday and Friday. Okay. All right. See you guys later.